Howdy, welcome back to AgEc 317. We're moving on with the second to last module, which is applied demand analysis. So last time we talked about production economics. Now we're moving on to the other side of the coin, which is demand analysis. So what we should be familiar with already from our other econ courses is demand in general. So just to start off with, quantity demanded, we say is the quantity of a good or service that consumers are willing and able to purchase, and an individual's demand of some good is the result of some utility maximization problem. So every single individual has a utility function that we never directly observe, but we can try and estimate the general shape and form of that utility function. And from that, we can infer their choices or their quantity demanded. And then we add all those individuals' demands up in a market, and we get market demand. So market demand is just the summation of all the individual demand curves across all individuals or consumers in a given market. Factors that affect demand, own price, the price of some good we're talking about, that's going to affect quantity demanded. Affecting the entire demand curve is going to be the prices of other goods. So other goods can act as complements or substitutes to the good that we're interested in. Expectations can affect demand, especially in the future. Taste and preferences, and there's really many other factors that affect demand. So we know all of that, right? That comes from our econ theory courses. So our job here in this class is trying to estimate a demand curve. And so how should we do that? So demand curves we've seen over and over again are these usually straight lines that slope downward. So in this case, we have a demand curve for cars. So on the y-axis, we have the price of vehicles in thousands of dollars, and then the quantity demanded of automobiles, in this case in millions. So this is the market here is all cars in the U.S. market. So if the average price of a car is really expensive, say around $45,000, then the quantity demanded at that really high price is going to be pretty low, right? Not many people are willing and able to buy a car at that price. Meanwhile, if cars are really cheap, so we can think of maybe the used car market, where you can find used cars maybe around $5,000 that are in pretty rough condition. Well, cars that are really low priced like that, there may be a lot of people who are willing or at least able to buy these really cheaply priced cars. And so this is just kind of generally the shape of the demand curve. Nothing surprising here. But again, we come back to the question, how do we estimate that? So that's nice, and we can make a lot of policy prescription based on the demand curve, but how do we get that demand curve? So as we've seen many, many times in this class, if we want to draw a straight line, what we need is data. And so we need little points everywhere of cars for a certain given price, and the number of people who actually purchase cars at that price. So if we have a lot of different individual observations, we can try and estimate this line. Cool. So in an ideal world, what we would need is lots of variation in price, and we need lots of people facing different prices, and also, real importantly, no feedback between price and quantity. So I'm going to go back a slide. Again, if we want to estimate this really nice line here, we would like to have little dots everywhere, these little dots, points of data. The more dots we have, the better we can usually fit this line. And so we need prices way down low, we need prices way up high, and we need people to face a lot of different prices. For cars, that may work out, but for a lot of goods, it may not. And so this is one of the fundamental problems of trying to estimate a demand curve, is that we rarely see customers facing large variation in prices. So for example, here's a demand curve for lattes, right? So at $4.50, Jack is demanding 12 lattes. Maybe this is per month, hopefully per month. Jill is demanding 18, and so the market demand at that price is 30. But if price of lattes are $2, well, Jack's going to demand a lot more, and Jill's going to demand a lot more. We add those up, and the market's going to demand Again, a lot more. But, and here's the big but, lattes aren't going to change prices very often. So let's say that we're trying to estimate demand for a single store. So if you've been to, let's say, Harvest in College Station, a really great coffee shop, they're going to price their latte around $4.50. And that's not going to change. It's not going to change across their 2 locations in College Station and Bryan, and it's not going to change over time very often. So I've been in College Station for a few years. You've been in College Station for a few years. The price of lattes at Harvest has never really gone down to $2. It's never gone up to $6. It's going to be priced at $4.50, and it's priced at $4.50 almost always. So what does that mean? Well, we see a lot of dots then. We see a lot of people demanding lattes at this one price, but it's going to be really difficult to observe what the demand is for these different prices because Harvest is not going to set, or hasn't set, the price of lattes very drastically except for $4.50. So they've priced it at $4.50. We're not observing a lot of other prices. And so all of these data points that would be nice to estimate this straight line demand curve just don't exist. And so what's happening is we're actually observing just market equilibriums. So you can imagine we are just observing this market equilibrium where lattes are priced at $4.50 and we're observing the quantity demanded at that price, right? And if it gets even worse, because if we fix supply, if we say this, the supply of lattes for Harvest Coffee is fixed, then the things that if we do see variations in price, it may be because demand has shifted. And if demand is shifting out, let's say from this green line to this blue line, then perhaps Harvest will respond by raising the price of lattes, and that's going to result in a new market equilibrium of a greater quantity demanded. Maybe demand shifts out again. Again, it may be just more people moved into College Station, higher demand. The price of lattes is going to go up. You can imagine if you've been to a coffee shop in a bigger city where there is much more demand, coffees are going to be priced higher. A latte is going to be priced higher in some coffee shop there than it is in College Station. So as demand is shifting out, we're going to see different equilibriums. We're not going to see points along this entire demand curve. We're just going to observe these individual points of market equilibrium. Okay, so what? Well, if we're just taking these single points here, this blue dot here, this blue dot here, this blue dot here, with the varying levels of demand, if we're fixing supply, try and estimate a demand curve giving just these 3 blue points. And what we're going to estimate, if we do a linear regression of these 3 blue dots, we're going to get this orange line. This orange line is not demand, right? It's supply. And so what happens is it's very easy, if we're just observing price and quantity observations, it's easy to just observe these blue dots, something like this. And if supply is relatively fixed and we try and estimate demand using just price and quantity, we're going to end up estimating supply. And so, again, this is kind of a more formal way to say that. If our quantity demand is just a function of price, that's going to be again, using just individual observations like these blue dots here, then it's going to be very easy to actually estimate a supply curve when we're trying to estimate a demand curve. Or even worse, if supply is not fixed, then we get some weird combination of the two that's going to mean essentially nothing. It's going to be very difficult to interpret. And so the reason for that, among other things, is what we call simultaneity. So simultaneity, we've talked about before in our discussion on endogeneity. So simultaneity is where price is affecting quantity demanded. Good, right? That's what we want to estimate. That's going to be our beta 1. But at the same time, price is affecting quantity demanded. Quantity demanded may also be affecting price. And so, again, let's go back to our Harvest latte example. If Harvest changes the price of their lattes and that affects quantity demanded, great. That's beta 1. We can try and estimate that. But if quantity demanded is changing for Harvest and they respond to that by adjusting their prices, then we have a two-way street of causality where P affects Q and Q affects P. And then if we just try and run this single model where each one of these affects the other, our estimate for beta 1 is going to be really biased, and it could be so biased that we end up estimating a supply curve rather than a demand curve. So this is a huge problem. And so estimating demand is actually not easy. It seems straightforward, but it requires some pretty complex models. So a few of the ones that are relatively common are what's called the AIDS model. It's the almost ideal demand system. The BLP model, Berry, Levinson, and Pakes. We can use instrumental variables and simultaneous equation models, or SEMs. These things are pretty advanced, and it's going to be beyond the scope of this class. So if you're interested in this, if you're interested in marketing, if you're interested in estimating systems of demand or demand curves, you need to go beyond this class. So what we're going to do for the rest of this class is ignore this problem of endogeneity. But if you're serious about this and you want to do good data analytics with demand curves or marketing, you're going to need to go further with econometrics. So if this does interest you professionally, I encourage you to keep taking econometric classes, try and take demand classes to do this the right way, because what we're going to do for the rest of this class is going to make some assumptions that essentially is not going to be right a lot of the time in the real world. So if you want to do this the right way, you're going to have to keep going. So I encourage you to keep doing that. But again, for now, we're going to ignore the endogeneity problem, pretend like it doesn't exist. We're going to try and at least minimize it, but we're going to look at markets with substantial price variation. And so, and we're also going to just assume that there is no simultaneity. That's a huge assumption. It probably is not okay. But again, we're just going to start with this simple approach. And if you're interested in doing this kind of work, keep going. Keep taking econometrics courses, and you'll get to a point where you can do some really, really cool stuff, and you can do it the right way. Okay. So that's a big caveat. Now we're going to go into this simple world where we're just going to ignore all these problems. Okay. So the law of demand tells us that the demand curve that we estimate should have a negative slope. Why? Well, that is just the law of demand. As the price of some good increases, the quantity demanded for that good should decrease, and vice versa. Okay, and we can try and test that with real data. So again, we're going back to this demand curve with automobiles. So some quick definitions. We said that the demand curve in generally is going to be quantity demanded as a function of price. We can represent this exact same function as price as a function of Q, and we call that inverse demand. Okay. So inverse demand is exactly the same as demand, but now we have price as the left-hand side variable. And so that just makes it easier to actually draw this line, because typically our y-axis is going to be price and our x-axis is going to be quantity demanded. And so to graph this in a nice, easy way, usually what we like to have is inverse demand. Okay, so movement along the demand curve is going to be a change in quantity demanded, and a movement of the entire demand curve is a shift in really anything else that is not price. Okay, and so, for example, if we're moving from, let's say we're at this outermost demand curve, and we move from this point to this point, that's a shift in quantity demanded. So quantity demanded is changing from 8 million cars to 10 million cars, as the price changes from $34,000 to $30,000. So cars are getting cheaper, and so quantity demanded is responding by increasing by 2 million cars. Okay, that's a change in quantity demanded. A change in demand is going to be a shift of the entire curve. So let's say that the interest rate in a car loan, that could definitely change the entire demand curve. So let's say with a 6% interest rate on that loan, we have this outermost demand curve. Now let's say that the interest rate increases to 8%. Okay, that means if you take out a car loan, the interest rate's higher. It might be more difficult for you to pay back that loan, or anybody in that case. So demand curve is going to shift closer to the origin. It's going to be a decrease in the demand curve. So now we're going from, let's say, this point here down to a new demand curve here. So our quantity demanded is not changing, but the entire demand curve is. So at the same quantity demanded, price is now going to decrease from $34,000 to $30,000. Another way to say that is at this price, $34,000, originally with a 6% interest, quantity demanded was 8 million cars. Now with the new interest rate, quantity demanded is going to be 6 million cars. Okay, that's a shift of the entire demand curve. So demand along for every single price is going to decrease as a result of this new interest rate. And if we have an even higher interest rate, demand is going to decrease even further. Okay. For a market, so a market, again, a market is just where we have a demand curve and a supply curve. The market equilibrium is where supply intersects demand, and the market equilibrium price is going to be the price at that point. The market equilibrium quantity demanded, or market equilibrium quantity, is going to be at the quantity at which those two curves intersect. And at any other price, we're going to have either a shortage or a surplus. So if in this case, the market equilibrium price is $25,000 for a car, if the price of cars, the average price of a car were to increase to $27,000, we're going to end up with a surplus, okay? Because at $27,000, there is a 12 million supply. So there's 12 million cars at that price where suppliers are willing to sell it, but people are only willing to and able to buy 7 million cars, which means there's a surplus here, right? So a surplus of 5 million cars, where sellers would love to sell their cars at this new higher price, but people are not as many people now are willing and able to buy cars at this new higher price. Vice versa, if we have a lower price than the market equilibrium, we're going to have a shortage. So if price decreases from say $25,000 to $23,000, then at that lower price, more people are willing to purchase cars, but fewer sellers are willing to sell at that price. So in this case, we're going to have a shortage of 5 million cars. Okay. Again, this is mostly just review. So comparative statics is when we fix either supply or demand, and then we change the other and see how the market equilibrium is going to change. So if we're going to hold supply constant and then shift demand in different ways, then we have what we call demand analysis. So if we fix supply at some level, the supply curve, that is, in this entire curve, we fix it, and then we just observe demand shifting, parallel shifts for different reasons, and we observe how the market equilibrium price and quantity are changing. That's essentially demand analysis. Okay. So how do we do that? So this should kind of ring some bells, right? So we have a demand curve here. Our original demand curve now is this light blue line with a 6% interest on your car loan. Now, what about people who face a 10% interest rate? Okay. You can imagine data structured so that an individual row can be an individual consumer. We can have a variable that is equal to 1 if that person faces a 6% interest loan, or equal to 0 if that person is offered a 10% interest loan. Right? That's a dummy variable. And the coefficient on that dummy variable is going to give us this vertical difference between the lines. And so then we can estimate the comparative statics here, how the change in market equilibrium price and quantity are going to change using a dummy variable, right? So that should be, and we can do the same thing with supply, do the same thing with both. But the important thing to remember here is that dummy variables are now going to be very important for our demand analysis, because that's going to be how we show parallel shifts in the actual curve. Okay, so we'll come back to the dummy variable in a second at the end of this lecture. Okay, so the next thing is elasticity. So elasticity is an important thing to measure. We've talked about this several times in class, so this should be nothing new. So I'll just let you read this motivation But in a formal way, our elasticity for anything is going to be percent change of y, if y is our left-hand side variable, given a percent change in x, our explanatory variable. Okay, and that simplifies to the derivative of y with respect to x multiplied by x over y. Okay, so we did this, you did this way back in AgEc 105 or your first econ courses. You could do this with a straight line by just calculating rise over run for your demand curve multiplied by the original quantity demanded divided by the original price, for example. Okay, that's fine, but that's going to be an approximation. So especially if demand is nonlinear in some way, this approach is only going to approximate elasticity. This new approach, where we're taking the derivative and then multiplying by this object here, that's going to give us the exact measure of elasticity. Okay, so this is a much better approach. So types of elasticities that we're going to really care about, at least for this module, is going to be own price elasticity, cross price elasticity, and income elasticity. We'll talk about all three of these in just a moment. But there are a lot of different types of elasticities. Really, almost anything you can make a model of, you can estimate in elasticity. So you can even estimate recreational behavior to sunlight or angling intensity to water clarity. So if water clarity improves by some percent, how is that going to change the percent of anglers going to fish? That's an elasticity measure. And so we can do that for almost really any economic system. So there's a lot of different types of elasticities, but again, the three we're going to focus on here is own price, cross price, and income. Okay, so own price elasticity, just as a quick review, own price elasticity, given the law of demand, is always going to be a negative number. So our percent change in quantity over a percent change in price should be negative because of the law of demand. So if we're just looking at the absolute value of this elasticity, we know it's negative. So if we're just looking at the absolute value of it, if it's greater than 1, we say that that's elastic, which means the percent change of quantity is greater than the percent change of price. If the elasticity is less than 1, it's inelastic. The percent change of quantity is less than the percent change of price. If it's exactly equal to 1, we say that's unitary elastic. If it's infinity, we say that that's perfectly elastic, or as it gets very, very, very large, it becomes very, very elastic. And if it's exactly equal to 0, we say that that's perfectly inelastic. Okay. So here's an example. We're actually not going to go through this. You can find the answers to this example in the description below or on eCampus if you're in AgEc 317. But just we'll set this up. So suppose that we're a movie manager at Movie Tavern, an awesome movie theater if you're in the Fort Worth area. So suppose that you want to estimate monthly demand for tickets as a function of the price of a ticket and the monthly subscription cost of Netflix and income. So we can imagine that the quantity demanded for tickets at Movie Tavern is going to be a function of price, right? So as the ticket prices change, that's going to affect quantity demanded. It could also be a function of Netflix. If the subscription of Netflix is very, very low, and Netflix has some great movie offers, and you might not want to go to Movie Tavern. This may be particularly salient now, since in this time of COVID-19, going to a Movie Tavern movie is now not possible. And so now the price of Netflix is going to greatly affect, obviously, the demand for Movie Tavern. And then income, obviously. So if your income changes, that's going to affect how many tickets you're going to buy over a given month at Movie Tavern. Okay. So given this, we should be able to calculate own price elasticity. If we assume some numbers for the price of a ticket, the price of Netflix, and income, we can estimate the exact own price elasticity at some given level. And then we can answer the question whether demand is elastic or inelastic. Okay. So when we have a linear demand function, is elasticity constant? No. So when demand is truly linear, we have elasticities it's gonna change along the demand curve. So now elasticity is now going to be a function of x and y. So if you're estimating a demand curve that's linear, meaning it's just Q as a function of P, or quantity as a function of price, and you're not doing anything to it, then the elasticity you're going to measure, you'll have to take a derivative of your estimated function and then multiply it by this object here. And so in this case, our y is going to be quantity, our x is going to be price. So the derivative of our quantity demanded, this is the partial derivative of quantity demand with respect to price, multiplied by quantity demanded divided by price. This elasticity measure is going to then be a function of where we are in quantity and price. So if the market equilibrium is way up here, then we have a really small x and a really big y, meaning that this elasticity is going to be a very small number, okay? And vice versa, if we're way down here on the demand curve, then the elasticity is going to be, the elasticity is going to be pretty small down here and pretty big up here, okay? So in general, this is the elastic range of the demand curve. The lower portion of a demand curve is inelastic, and the exact midpoint is going to be our unitary elastic point, okay? So if we have this linear demand curve, then elasticity is not constant, okay? It very much matters where you are along the demand curve. But as we've seen with many of the models we've made so far, a linear model is often not the best model. And so we would often like to, or allow at least demand to be nonlinear. And when that's the case, we'll see in a log-log model, we'll see demand be nonlinear. And when that's the case, we're just allowing this straight line to bend a little bit, like that, or like that, maybe. And when we allow it to bend, we often get a better model fit. And when we do that, elasticity then perhaps will be just a constant number. So that could be a nice thing. We'll see that in just a little bit. Okay, so if we can relate our elasticity to revenues in a pretty cool way. So remember that we can calculate our inverse demand, which is price as a function of quantity. So then total revenues, which is just price times quantity, right? We know that that's true. But then this price here, if we write price as a function of quantity, which is our inverse demand curve, and then multiply it by quantity, that is our total revenue, right? Still. But now everything is in terms of Q. Marginal revenue is by definition the derivative of total revenue with respect to Q. So if we take this new definition of total revenue and take the derivative with respect to Q, we get this function here. So the derivative of price, this inverse demand with respect to Q times Q plus P. So this is a good, if you want to practice up your derivative skills, this is the answer to this. So the partial derivative of total revenue with respect to Q is this function here. We can rearrange things using algebra to this function here. And then further, we can simplify it using the definition of an elasticity into this function here. So marginal revenue is going to be price times 1 plus 1 over the ohm price elasticity. Pretty cool, right? So this is a pretty cool little function. And so we can look at it and make some pretty cool observations. So again, if marginal revenue is price times 1 plus 1 over the ohm price elasticity, and remember that ohm price elasticity, this is always a negative number because of the law of demand. If it's not negative, we have some problems. We have a violation of the law of demand, which is a big issue. So this is a negative number, right? So that means we're going to have 1 minus this amount here, if this is always negative. So if this elasticity is less than 1, let's start with this inelastic case. If it's less than 1, then this little portion here, this component is going to be greater than 1, this whole fraction. If that's greater than 1 and we're subtracting it from 1, then everything in parentheses here is going to be negative. Okay? If everything in the parentheses here is negative and we're multiplying it by price, which is always positive, then we get a positive times a negative, meaning this whole thing is negative, meaning marginal revenue is negative. Okay? What that means is if we have inelastic demand, marginal revenue is going to be negative. So if we're on a linear demand curve and we calculate our elasticity at some market equilibrium and we come up with an inelastic demand, then we know that our marginal revenue is negative. Okay? Vice versa, if we calculate our demand and it's elastic, our marginal revenue is going to be positive, right? Cool. So that's why, right? It's just this, if demand is elastic, marginal revenue is positive. Why is that true? We just need to plug in the values here and we see that it's just mathematically true. Okay, here's a lot of words. And essentially, it's just a lot of words that, let's just focus on this last sentence, okay? So I encourage you to read this whole thing, but the takeaway here is that when demand is elastic, reductions in price are going to increase revenue. Okay. Again, if we estimate elasticity of demand, own price elasticity, and we get an elastic demand, then if we put our good, whatever good we're talking about, on sale, that's going to increase our revenue. Okay. So in that case, you should put your good or service, whatever you're selling, on sale. It's actually going to increase your revenue. Okay. When demand is inelastic, if you decrease your price via a sale of some kind, or some kind of marketing promotion, then that's going to decrease your revenue. Okay, so that's not a good idea. So when we calculate elasticity, whatever number we get for that can inform us about how we should adjust the pricing of our good. So let's say that we're selling Bluebell ice cream, okay, and we estimate that demand for Bluebell ice cream is inelastic. Okay, so if we put Bluebell ice cream on sale, that's going to decrease our revenue. That's a bad thing. We don't want that to happen. So if you're Bluebell and you calculate an inelastic demand, then you should either keep the price the same or raise it. If you raise the price when you have inelastic demand, that'll increase revenue. Okay. So again, you should know that from previous classes, but the reason why is actually this mathematical equation here. Okay. So let's go even one step further. So if we know that marginal revenue is this function here, and again from our early econ classes, we know that at least in the case of a monopoly, if you're the only seller, then the optimal price and quantity for your market, if you're a monopolist, is to set marginal revenue equal to marginal cost. So if we set this function here, marginal revenue equal to marginal cost, and rearrange, what we can find is at that optimal point where marginal revenue equals marginal cost, the optimal price is going to be equal to marginal cost divided by this number here. Okay? So if we know our elasticity, own price elasticity, and we know marginal cost, we can solve for the optimal price. Okay? That means we can solve for exactly how much we should be selling our product for. Okay? So here's an example. So suppose that our marginal cost to produce a fly fishing reel is some constant number at $25. And suppose that we calculate demand elasticity or own price elasticity as -2. So what is the optimal price of a fly fishing reel? So I'm just going to jump back. We can solve this really quickly. Marginal costs are constant at 25. It's going to be 25 divided by 1 plus 1 over -2. That's 1 plus 1 over -2. So that's 1 minus 1/2, which is just 1/2. 25 divided by 1/2 is going to be 50. Okay. So in this case, if we've estimated demand elasticity to be -2 for fly fishing reels, and it's some constant number here where every time we produce a reel, it costs us $25 to do so. If that is all true, then the best price for a fly fishing reel, in this case, if we're a monopolist, is to price that fly fishing reel at $50. Okay. Cool. So, okay, well, actually, before we move on to cross price elasticity, so that's all really great, right? It's assuming that we're in a monopolist situation or we have at least a differentiated product. But again, to do all this, we need to know our elasticities, right? And so we're going to keep talking about elasticities here, but we're going to return at the end to how exactly we estimate those. That's going to be a really important step. Okay, so for cross price elasticities, this is the percent change in quantity demanded for some good A given a percent change in the price of B, some other good B. And that is represented just by this equation here. The partial derivative of quantity demanded for good A with respect to the price of good B multiplied by the price of good B divided by the quantity of good A, quantity demanded of good A. Okay. Again, as a quick review, if the cross price elasticity is positive, then the two goods are substitutes. If the cross price elasticity is negative, the two goods are complements. Okay. Substitutes, if you're big into cooking, you think about red peppers or red bell peppers and green bell peppers. They taste about the same, so you can usually substitute one for the other and be okay. This might be a little more controversial, but if you have onions and shallots, again, you may be able to substitute one for the other, although some hardcore cooks or chefs may argue with that. Complements, these are things that go together. Peanut butter and jelly, classic things. So if the price of peanut butter goes down, quantity demanded for peanut butter is going to increase, right? It's a law of demand. If the quantity demanded of peanut butter increases, so should the quantity demanded of jelly, which means as the price of peanut butter goes down, quantity demanded of jelly should go up, right? That's why that cross price elasticity is negative for complements. And I see this a lot. If you wear an Aggie polo and light blue jeans, those things seem to always go together. So I would probably, I think it's safe to assume that those are complements. Complement with an I is this. You're doing great. And you are. If you're following along and you're in AgEc 317, pretty impressive work so far. Okay, and then the last elasticity we're going to talk about is income elasticity. So that's just going to be the percent change in quantity demanded given a percent change in income. So we can write that as the partial derivative of quantity demanded with respect to income multiplied by income over Q, right? If that income elasticity is between 0 and 1, we consider that a necessary good. If the income elasticity is greater than 1, we consider it a luxury good. Both necessary and luxury goods are considered normal goods. Okay, so that's the larger group here is normal. And if the income elasticity is negative, then we call that an inferior good. Okay, so necessary goods, things like insulin, water, rent, those are usually necessary goods. Luxury goods, perhaps phone cases, subscription services, things like that. And then inferior goods are things where if your income is increasing, you're going to spend less money on it. So personally, that's baloney for me. But maybe you like baloney. I don't know. Okay, here's another example. Again, we're not going to go through the exact answers, but you should be able to do this, and the answers are going to be posted along with this video. Okay, so great. We can do some really cool stuff with elasticities, but how do we actually do that? So we're going to go back to our nonlinear models here and think about the 4 different types of log models. Okay, so we have linear models where we're not doing anything. This is just a typical linear model. We have linear log models when we're taking the log of the right-hand side variables, log linear models, and then log models. Okay? So if you have a linear model, ohm price elasticity, for example, is going to be the partial derivative of quantity demanded with respect to the price of that good multiplied by the price of that good divided by quantity demanded of that good. Okay? So in this linear model, where we're just keeping everything as is, then our ohm price elasticity is going to be beta 1, whatever we estimate for beta 1, multiplied by P over Q. Okay. Similar calculations for cross price and income elasticity. For linear log models, that is where we keep quantity demanded linear and we log the other variables on the right-hand side. Then the partial derivative of Q with respect to P1 multiplied by P1 over Q1. If you do that derivative and simplify, you'll find that ohm price elasticity is going to be our estimated beta 1 divided by whatever quantity we're at. Okay? Similar for cross price and income elasticities. Log linear models, again, if you're able to take the correct derivatives, this is going to simplify to beta 1, whatever we estimate for beta 1, times the price of good 1. Similar for cross price and income elasticities. And then the easiest one is where we have log models. That's where we take the log of both sides here. And at least in the ohm price elasticity case, if we're taking the derivative of all this with respect to P and then multiplying by P over Q, what we're getting, that eventually simplifies to just beta 1. Okay. So we've talked about that before. In log models, we are estimating the elasticity directly. So it should come as no surprise here. Okay, so back to reality. So everything we've talked about in estimating these kind of demand models, I'm going to go back a slide, we have Q as a function of price, which we talked about early in this lecture is not a good way to do that. That's almost certainly going to result in a biased estimate for beta 1 and actually a biased estimate for all of the other coefficients as well. So it's not a good way to do it, even though we are doing it here. We're just assuming that it's okay, even though in reality it's not. So even though we're not currently able to use the tools to get around this type of bias, we should still be able to look at the results from these more advanced models and still use them in our demand analysis. Okay, so here's some results from a somewhat famous paper on light beer. So here is a table of estimated own price and cross price elasticities for 5 different types of light beer using real demand data from the 90s. Okay, so this is typically what you're going to see in academic papers or how a lot of analysts present their results. It's just kind of a big table that can be pretty intimidating. What we're going to focus on is this diagonal here. So how to read this table is, these are just the coefficient estimates. So this is the percent change in quantity demanded for Genesee Light given a percent change in the price of Genesee Light. Whoops. That is by definition own price elasticity. The estimate for that is negative 3.763. Okay. Of course, it's negative, right? That's what we expect for own price elasticity. And it's 3.763, which means that it is elastic. Okay. What does that mean? Well, if you are a manufacturer for Genesee Light, you've estimated an elastic demand given the current conditions. What that means is if you put Genesee Light on sale, then you're going to increase your revenues. Okay, so the result here, at least for Genesee Light, because demand own price elasticity is elastic, putting Genesee Light on sale is going to increase your revenues. So it's a good idea to put it on sale, or at least it is okay if you put it on sale because it'll increase your revenues. As it turns out, own price elasticity for Coors Light, own price elasticity for Old Milwaukee, whatever is just this generic light, and Molson Light, all of these actually turn out to be elastic. So all of these beers, if they're put on sale, is going to increase revenue to whoever's selling them. Cool. The other thing to look at, let's look at now this Coors Light. We're going to look at the percent change in Coors quantity demanded for Coors Light given a percent change in Genesee Light. That is predicted to be 0.569. Positive 0.569. That means this cross price elasticity is, again, it's a positive number, which means that Coors Light and Genesee Light are substitutes. Okay? Which means that if the price of Coors Light were to increase, that means the quantity demanded of Coors Light is going to decrease, and that decreased demand for Coors Light is going to shift over to Genesee Light. Okay, so if Coors Light gets more expensive, we expect more people to buy Genesee Light. Okay, so again, what that means is if you are Genesee Light, or at least let's say that you're Coors Light, and for some reason you need to adjust your price by increasing it. Maybe there's some supply problem. You're increasing your supply. You can expect some of the people who were buying your beer to shift over to Genesee Light. And actually, the cross price elasticity of Coors Light with respect to Genesee, Old Milwaukee Light, and Molson Light, they're actually all positive, these cross price elasticities, meaning that Genesee, Old Milwaukee Light, and Molson are all substitutes for Coors Light, okay? Which makes sense, right? And if you read the paper, it makes a lot of sense. It's a pretty competitive market, so if the price is changing here, people are going to shift their demand to really any of the other light beers, okay? The last thing to talk about here is the numbers in parentheses are the standard errors. This is generally how results are presented in the real world. So we get a point estimate here, which is our elasticity, and then the standard error of that elasticity. And if we go way back to Module 3, we know that the t statistic is calculated by taking our coefficient and dividing by the standard error. And if we compare that to the t critical value, which is around 2, if that number, again, our beta, this coefficient divided by the standard error, if that is greater than positive 2 or less than negative 2, then we get a significant result, meaning that this coefficient is significantly different from 0. Okay, so let's take the Genesee Light, for example, this negative 3.763 divided by 0.72. It's a big number, okay? It's ballparking going to be somewhere in the tens, negative 10, and that's going to be a lot less than negative 2. So we say that this coefficient here is, or this elasticity is significantly different from 0, okay? It's a quick way to read this table without having to actually have p-values in front of us. The standard error is actually all we need if we just assume a t-critical value of around 2, okay? Okay, so let's go through an actual example. Again, we're going back to this more simple world where there's probably going to be simultaneity and endogeneity. But let's estimate a demand system for apple juice. Okay, so we have demand for apple juice data. So specifically, we have this kind of large data set here of demand for apple juice. Just quickly going through the variables, we have column A is just an ID. So each row here is going to be an individual. So this is one person on one occasion that purchased apple juice. Okay, and if we just quickly jump to the bottom of this row column, we see that we have about 2,400 observations. So that's 2,400 observations of people purchasing apple juice. Okay, so this first column is quantity of apple juice that was purchased or demanded. So this is going to be in liters. So some are are pretty big. So here we have this ninth person purchased 6.5 liters of apple juice. It's a pretty large amount. Meanwhile, the seventh person bought half a liter of apple juice. So apple juice, as you know, comes in a lot of different sizes. And so this first column is how much apple juice an individual purchased. This third column here, the price of apple juice, is in dollars terms, dollars per liter, how much the apple juice cost of that person purchased. We also have information on the price of cider. So at the same purchase decision, so if this is a Tuesday of last year where a person purchased apple juice, then at that same time, this column D represents the price of cider at that same time. We also have the price of cranberry juice and the price of soda. All of these are in dollars per liter. So we got the price of three goods that could be related somehow, right? Either complements or substitutes. We also have income of the individual. So this third individual had an income of $32,500 per year. We have the size of the household of the person who made the purchasing decision. So if this third individual has a household size of 2, this fourth individual here has a household size of just 1. And if we skip down to 10, that person has a household size of 7. Okay, then we have 4 different dummy variables here that indicate children. So this first one, let's just expand it for a second. This is children under 6. It's a dummy variable. Equals 0 if the household has no children under 6. Equals 1 if there are children under 6. It's not a count of how many children. It's just, do you have a child under the age of 6? The second one here is a dummy variable equal to 1 if the household has any children age 6 to 12. Third one is, does the household have any children age 13 to 17? And the final one is, do you have any children in the household who are 18 and older? Okay. There's an omitted category that just isn't labeled here, and we just have to think about it a little bit. So what does it mean for a household to not have a child under 6, not have a child from 6 to 12, not have a child from 13 to 17, and not have a child that's 18 and over? That is, what if columns I, J, K, and L all equal 0? Well, that means that household has no children. Okay, so the omitted category here is no children. All right, so if we include all these dummy variables, it's important to remember that the omitted category here is not a variable that has been included, but we know it's kind of implicitly included, which is that an additional dummy variable that equals 1 if the household has no children whatsoever. So yeah. Okay, in a similar way, we have 3 dummy variables on the marital status of the household. So first we have married, dummy variable equal to 1 if the head of the household in this purchasing decision is married, equal to 1 if they're not married. Widowed equals 1 if that person is widowed, 0 otherwise. And divorced equals 1 if that person's divorced, and 0 otherwise. So what does it mean? For example, this fourth person here is not married, not widowed, and not divorced. Well, if you're none of those things, then you're single, legally speaking. So the omitted category here is single. So if we include all these dummy variables, then it's important to remember that the base category here is single. Okay. And then we have a bunch of additional categories that we're not going to use here, but feel free to if you'd like. These are geographic indications. So for each individual observation, we have dummy variables of where that purchase was made. So we have the categories here are New England, Mid-Atlantic, East North Central, West North Central, South Atlantic, East South Central, West South Central, and Mountain. So might be difficult. It's a lot of categories. The omitted category here is the Pacific. Okay, so think California or Oregon or Washington. So that's the base category. So all of these dummy variables, these geographic indicators, are going to be relative to the Pacific region. Okay, So we're not going to use those now, but feel free to play around with that to see if demand changes based on your region. Okay, so a lot of data here. This is one of the bigger data sets that we've worked with. So what are we going to do? Well, let's go ahead and estimate the following model. Okay, we're going to do a log-log model. So the log of quantity demanded is a function, again, log of quantity demanded of apple juice is going to be a function of the log of the price of apple juice, the log of the price of cider, the log of the price of cranberry juice, the log of income, and then we're going to include these three marital dummy variables, okay? And again, remember that the omitted category here is single, okay? So we're going to need to create a lot of these variables. The dummy variables are created for us, that's fine, but we don't have the log of any of these, so we're going to have to create the log of quantity demanded, log of the price of apple, log of the price of cider, log of the price of cranberry, and log of income. So we'll go ahead and do that quickly. So we're going to have to create several new variables. Eventually the log of quantity of apple, log of the price of apple, log of price of cider and cranberry. Those are all next to each other, so I'm just going to go ahead and create 4 new columns here. Going over to the Home tab, then over to Insert. 1, 2, 3, 4. Okay. I'm going to call this natural log of quantity demanded. This one's going to be the natural log of PA, I'll call it the price of apple juice. Natural log of the price of cider, CI. And the natural log of the price of cranberry, CR. Okay. So for the natural log of quantity of apple juice, I'm just going to say this is equal to the natural log of Q apple. Okay. For the natural log of the price of apple juice, I'm going to say this is equal to the natural log of the price of apple juice. Natural log of the price of cider is going to be equal to natural log of the price of cider. And the natural log of the price of cranberry juice is going to be equal to the natural log of cranberry juice. Pretty straightforward, right? This looks a little concerning, right? The natural log of Q here is a 0 value. That's okay. That's 0 is a value that exists. The reason is because the quantity demanded here is 1. The natural log of 1 is 0. That's always the case, okay? That's okay. The problem would come is, would happen if the quantity demanded of apple juice was 0. So I'm going to skip all the way down to the bottom here. And way down here, I'm going to say, what if quantity demanded of apple juice is 0? And we try and take the natural log of that. What is the natural log of 0? It does not exist, okay? It approaches negative infinity, but it's not a number that actually exists. So that would be problematic. In our data here, we don't have any 0 values. These are all purchases, so someone made some positive purchase of apple juice, so we're okay. Okay, so we're going to just go ahead and copy this for the rest of the column. We get all our good natural logs here. So we're almost done, but we still need to create the natural log of income and then include these dummy variables, okay? And remember that in Excel, we need to have all of our right-hand side variables next to each other. So I'm going to create 4 more columns, 1 for the natural log of income, and then 3 more for our dummy variables, okay? I'm going to call this the natural log of income. And then here are going to be our dummy variables. So let's go ahead and just move the dummy variables over. We have married, widowed, and divorced. I'm just going to select all 3 of these and hit Cut or Control X or Command X and just move them over to the right place, okay? Easy enough. And for the natural log of income, we need to create this. Is going to be equal to ln of income, way over here. Okay. And copy that for the rest of the column. And there we go. We have all of our data that we need. Natural log of quantity demanded of apple juice as a function of the log of the price of apple juice, log of the price of cider, log of the price of cranberry juice, log of income, and then these 3 marital dummy variables. So we're good to go. We're ready to run the regression. At this point, this should be almost second nature. Go to our data tab, data analysis, regression. For our y range, we're going to select the natural log of q. Okay. For the x range, we're going to select the natural log of the price of apple juice all the way through these 3 dummy variables. Okay. Labels, and we'll send it to a new worksheet. Hit OK. And there we go. Our regression. So I'll zoom into the results here. Let's zoom out a little bit. Okay. So we'll look at the same things we always look at. What is the adjusted R squared? 0.09. That's not great, right? That means that our variables here, 1, 2, 3, 4, 5, 6, 7 of these variables are explaining about, well, 9.5% of the variation in the log of the quantity demanded of apple juice. Not great, potentially concerning, and we can play around with different models to try and fit a better model fit, or just think a little bit harder about what we think demand for apple juice really looks like and create a better model. So right now, again, the model's not great. It's probably worth going back to the drawing board and thinking of a better model. For now, we're just going to stick with it, knowing that this isn't exactly the greatest fit. Okay. Okay. The p-value on the f-test, very significant, meaning that at least one of our explanatory variables is significant. That's good. And if we look at the p-values, we see that the intercept, natural log of the price of apple juice, those are the only 2 that are significant at the 5% level. Okay. Natural log of income is significant at the 10% level. I'm going to go ahead and highlight it for now, but it's not significant if our alpha is 0.05. So just keep that in mind. Okay, so what does that mean? Let's look at it. So the natural log of the price of apple juice, this coefficient is negative 0.986271, right? That is an estimate of the elasticity, the own price elasticity of apple juice. Okay, so you should recognize that it is, technically, it is inelastic, right? It's negative. Own price elasticities are always going to be negative. It is slightly smaller than 1, which means it's inelastic, but it's also very close to 1. So it's almost unitary elastic, which means that the way we'd interpret this coefficient is if the price of apple juice increases by 1%, then quantity demanded will decrease by 0.986%. Okay? So it's almost 1, meaning that as the price of apple juice goes up by 1%, quantity demanded should go down by almost 1%. Okay? All right. The price of cider and cranberry juice are both insignificant here, meaning that they're not really either complements or substitutes, at least according to the data. I mean, we would think that cider might be a good substitute for apple juice. Whenever you have apple juice, it seems logical maybe that you'd be able to substitute in cider instead. But we get, first of all, an insignificant result and slightly negative, which means really we should consider this just to be 0, but if we do take it as face value, it's kind of slightly a complement, which is not what we'd think. So again, it seems like the price of cider is not really affecting the price of apple juice. Could be a lot of reasons for that. Some of those reasons could be because of the way we fit the model, but it also could just be some logical reasons. Maybe cider is much more seasonal, and this data was taken in a time like July where there was not much cider available on the market, and so it's not doing much to affect the demand for apple juice, which is relatively unseasonal. You can get apple juice around any time of the year, right? Cranberry juice, also insignificant, so it's neither a complement or a substitute for apple juice. It would be, maybe it'd be interesting if there's cran apple juice, different juice mixes. That might be a nice, if we had data on that, it might be nice to include that and see if that is either a complement or substitute for apple juice. But as we've included these two different juices, neither one of them are either complements or substitutes. So if you are selling apple juice and the price of cider and cranberry juice is going crazy, according to this data, you really shouldn't be too concerned. Okay, so if the price of cranberry juice, for example, went up like crazy, so maybe perhaps there was some failure in the cranberry supply one year, that huge decrease in supply resulted in a massive spike in the price of cranberry juice, and you're an apple juice seller, you're worried, okay, is that going to affect demand for my apple juice? According to this data, no. So if the price of cranberry juice jumps way high, it's not really going to affect the quantity demanded of your apple juice. Okay. Income is almost significant. It's not quite. So if we just pretend it is significant, if, for example, we set our alpha at 0.1 instead of 0.05, then this coefficient is 0.0716, which is in between 0 and 1, meaning that apple juice is essentially, again, according to this data, a necessary good. Okay, it's a normal good because it's positive, and because it's between 0 and 1, that means it's a necessary good, which, again, you may or may not believe according to the data. If our alpha is 0.05, then this is not significant. That means that income really has no effect on the price of apple juice. Okay, so if your income is going up by a lot or going down by a lot, this model says that you should be buying about the same amount of apple juice regardless of that income change. Okay, and then these three coefficients here are on the dummy variables. The omitted category here is single, so I'm just going to write it down here. Single, again, is the omitted category. None of them are significant. What does that mean? That means that if you're married or widowed or divorced, you don't demand any significantly different amount of apple juice than if you were single. Okay, so essentially, again, what this model is telling us is that your marital status does not have an effect on how much apple juice you're purchasing. Okay, maybe surprising, maybe not, but that's what the data is telling us. Now, just for the sake of example, let's suppose that this divorce coefficient is significant. Okay, again, it's not, but if it were significant, how do we interpret this? Well, remember that this, I'm going to flip back to the model. This is in terms of the dummy variables are linear, right? We didn't do anything to them, we just kept them as they are. And the quantity variable here is logged, which makes this a log linear model for the dummy variables. And if we go, remember our model specification lecture, this really key table, we are looking at let's zoom in here a little bit, a log linear model, right? So how do we interpret the beta? A 1 unit increase in our explanatory variable results in a beta 1 times 100% increase or decrease in our dependent variable, right? It's always good to remember that. So if we go back to our results, if we were supposing that this coefficient was significant, what this would say is that divorced households, on average, are consuming 15.6% less apple juice than single households. Okay. Again, this is relative to the omitted category, which is being single. And we interpret this, to interpret this log linear model, we need to multiply it by 100, right? So again, that is, this coefficient means if it were significant, that a divorced household would consume, on average, 15.6% less apple juice than single households. Okay? All right. But again, it's insignificant along with these other three, meaning that there is no significant difference between married, widowed, and divorced households relative to a single household. Okay? Okay. And that's it. We've estimated that model, and we're able to make some pretty cool decisions. The final thing to talk about is going back to this coefficient here on the price of apple juice. The own price elasticity is 0.96271, which again is technically inelastic. So what does that mean from a marketing standpoint? If we were to put the price of apple juice on sale, which means we would reduce the price of apple juice, and because demand is inelastic, if we did that, we should expect a decrease in our revenue. Okay, so let's suppose that you're H-E-B and you're selling apple juice and you have the same data and you observe and estimate own price elasticity to be inelastic, like it is here. If that's the case, and you put apple juice on sale in your store, then your revenues are going to go down because of that. Okay, so it's not a good idea to put apple juice on sale. You would either want to get more data continuing to sell apple juice, maybe think of doing this every quarter, estimating your elasticity of apple juice every quarter or every month, maybe every week, and seeing how that elasticity changes. Whenever that elasticity jumps to 1 or above, then your elasticity will become elastic. And in that case, you can put your apple juice on sale, and that's going to increase your revenues. But as long as apple juice exhibits inelastic demand, putting your apple juice on sale is a bad idea. Okay. So cool. So that's essentially the kind of the big takeaway from this model, because most of everything else is insignificant. All right.